prime second derivative of x star. All right, can you read that? F second derivative evaluated x star. And let's not overkill this. X star is a point between the x you have in mind and x naught. In other words, by the mean value theorem, we can find that the remainder term can be written in this form. So here's an equality, Taylor series with a remainder. Now, let's take expected values. First, let x naught be the expected value of x. All right. Then, let's calculate the expected value of f of x is equal to f of x naught, which is the expected value of x, plus, well, this is just some term that depends on x naught, but this is random, and this is expected value of x minus x naught times f prime of x naught plus this term. But now we notice that expected value of x minus x naught is 0 because of the assumption. We're expanding this function around its expected value. So this becomes 0. And look, x minus x naught squared is non-negative, so the expected value of it is non-negative. So this is greater than or equal to 0. And this gives you the desired result. Expected value of f of x is this plus something non-negative, so it's greater than this. And that's Jensen's inequality. Now, let's see all the good things that happen from it. First, just some examples having nothing to do with information theory. If f of x is x squared, we get the well-known result that the second moment is greater than the first moment squared. Two, if f of x equals, say, e to the x, we get the fact that expected value of e to the x is greater than e to the expected value of x. In fact, using only this, we can prove this result, 3, let mu sub r equal expected value of x to the rth moment, 1 over rth root. And there's a tricky little way in 2 lines or so to prove that mu sub r, the rth moment, is monotonic in R. There's a special case. So in particular, The second moment, well, it's called the Arth mean. When R equals 2, you get the RMS inequality. When R equals 0, you get the geometric mean. When R equals -1, you get the harmonic mean. So the harmonic mean is less than the geometric mean, is less than the arithmetic mean, is less than, et cetera, et cetera. So if you're curious about this, come by during office hours or something, or look it up. Because that's nice. By the way, what's the role of entropy in all of this? Well, believe it or not, if the function is log 1 over p of x, where p of x is the underlying distribution, then the entropy is the expected value of log 1 over p of x. And it turns out that the entropy plays the role of the not the harmonic, the geometric mean. Geometric mean. When R equals 0. Okay, now let's prove theorem. I hate to call them theorems, maybe proposition, something less exalted. D, P, Q is greater than or equal to 0. Proof via Jensen's inequality. The relative entropy distance of P to Q. Why do we call it relative entropy? Because, where was it written? Nowhere we can see. This is summation P log P over Q. So without the Q, it's the entropy. So you could think of it as the relative entropy of P with respect to some other probability mass function. It also is the expected log likelihood ratio between two hypothesized underlying distributions for the data. Now, what's it called? Well, this came up in the work of Kuhlbach and Liebler in the 50s, so it's called the Kuhlbach-Liebler information number. So that's a highly used name for what we're calling relative entropy. It's also called the information for discrimination in the PhD thesis and subsequent work of Imre Cizar. All right, let's prove it. Let's look at minus D PQ. This is the advantage of trying to prove it before class in finding that Jensen's inequality goes haywire for plus D. I'll show you one. This is equal to summation P of X, let's say, log Q of X over P of X. See, I just flipped these, changed the sign of the log. And this is for X where? All right, let A be support set of P. So this is X in A. We only take the terms for which P is positive for the expected value. All right. This is the expected value of log Q over P, which is less than or equal, by Jensen's inequality, since log is concave, log of the expected value of Q over P. But the expected value of Q over P is summation P times Q over P. The P's cancel, so this becomes summation of Q of X, where X is in A as before. Now this is log of the summation of Q of X. But notice, summation of Q of X, which if we hadn't kept track of the support set, would have been 1 if they both had the same support set. Here it's less than or equal to 1. Aha! So log of a number less than 1 is negative. So this certainly is less than or equal to 0. In fact, it's equal to 0 if P equals Q. All right, so we have now shown that minus D is less than 0, or D is greater than 0. Okay? And that was by Jensen's inequality. We've actually shown more, because this is, note, since log P, log whatever it is, Y is strictly convex, concave in this case, D equals 0 if and only if the function is equal to its mean, which is if only if P of X equals Q of X for X in A in the support set of either. Now, I haven't defined strictly concave, but there is a limit here. Because we're not doing Jensen's inequality, we're doing information theory. By strictly concave, I mean that the tangent line hits only in one point, and is this is strictly convex, and something with a flat spot in it is not strictly convex. By strict you can go through the proof and show that log P over Q must be a constant for you to have D equals 0. And if so, then P over Q is a constant. But summation P equals 1, summation Q equals 1, so therefore P equals Q.